Hi, my name is Trevor Whitford, and today we did Lab 6, which illustrates Charles' laws, which is a direct relationship between the volume a gas takes up and its temperature. And so we illustrated that in this lab utilizing crushed ice and water, hot water, and this syringe with a cap. It's a 10 milliliter syringe with 12 milliliter capacity, but we filled it up halfway to the 5 milliliter mark. So this lab was really simple. It was fun. I felt a little inconfident toward the end with my results, but ultimately they illustrate the relationship between temperature and volume. I figured that there was going to be more of a significant difference, but I can go into the data. So we took this, filled it up with 5 milliliters of air, and we made sure it was comfortable. And then we submerged it into hot water for 30 seconds. Before we did that though, we did measure the temperature of the room by holding this thermometer out for 30 seconds, gauging the temperature of the room, in which we read 24.9 degrees Celsius. After the 30 seconds has finished with the syringe in the hot water, as we hold it down, we push it to see how much volume has changed. So even in that short time, we went from 5 milliliters to, this is about 5.6 milliliters. So if we had gone the full 30 seconds, which we did in the experiment, we got 6 milliliters after that 30 seconds. This is really cool because what it does is this is I guess like the equilibrium. So you have the hot water, you have the air or the gas, and then you have this container. So the air wants to fill the container, then the environment is the hot water. So you submerge it, and so eventually the container and the gas will rise to the same temperature eventually, but in the 30 seconds it didn't quite do that. But yeah, we even got it closer to 6 that time. That's about 5.8 holding it in there. But we got 6 milliliters, and the water itself is 79.8 degrees Celsius. And then we waited a little bit for this to hit room temperature. Don't necessarily think that's necessary, but we did. And then we submerged it into the ice water. This is crushed ice. Let's put some ice and put it in a bag and then crushed it up. Put this in here for 30 seconds. Now the water itself is 1.5 degrees Celsius, and our end result, this is kind of where I was unconfident, was we got 4.8 milliliters as our end result after the 30 seconds. I really expected a significant difference. But ultimately, this does illustrate Charles' law. It's V1 over T1 equals V2 over T2. So I'm just gonna hold it in here for a couple more seconds, see if I can illustrate this in person. Okay, let's see. So originally 5 milliliters. So even then, I guess we didn't let it sit out and get the become temperature, the room temp, but we're back at 5 milliliters after maybe like 10-15 seconds of submerging it in here. So unfortunately, we only got 4.8 milliliters, but I was okay with that because one, I believe I conducted it correctly, and two, it illustrated the relationship between the volume that the air takes up and the temperature. So the reason why it does that is because the atoms are more and less kinetic dependent on temperature. So you heat up molecules, the atoms become more kinetic, and so they move around and they take up more space. It's kind of like when your tire is looking pretty full on a summer day, but whenever it becomes cold, right? So now that the atoms are less kinetic, it appears to be decompressed, but it's just that the atoms are more dense and not scattered around. So they have they don't take up as much space, and so therefore maybe in the wintertime your tires might need look empty. So that's that. Once again, this was Lab 6. This is Charles' Law, or Ideal Gas Law. And my name is Trevor Whitford. My student ID is 7263931. Thank you very much for your time. I hope I was able to adequately illustrate the principles in this lab. It was really great, and thank you so much. Bye-bye.